All right, chemists, let's get started. Hopefully everyone had a really relaxing break. We just have a little sprint here until the end. I think there's 5 more classes left. So it's kind of like, looking into a sunset. We know it's going to happen. It's going to end. So let's just enjoy our time here together, what little time we have left. All right, so we left off talking about gases in chapter 10. We'll finish up here in chapter 10. We'll start chapter 11. There's a couple more chapters to go, but they're fairly short. They're fairly short, and I have most of the blanks in the slides already filled out for you so we can get through it faster. Actually, before I get started, I wanted to announce that I decided to have my Zoom review session on, I think it's Thursday, December 8th at 6:30 p.m. in this room. So that's reading day. It's reading day, like a Thursday, at 6:30 in this room. It's same stuff, Zoom. I'll have a document. It's on the calendar. I just haven't made the documents yet. All right, so do be prepared for that, but just earmark that day for the review session, and it'll be recorded. I'll post it. I think there's still a couple more days until your guys's final exam, so you'll have some time to study there. All right. Okay, that's out of the way. All right, so we left off talking about real gases. The previous classes, we talked about ideal gases, where we just use PV equals nRT. Basically, we said, depending on the number of moles of gas we have, directly correlates to the volume that they occupy. It doesn't matter what the identity of that gas would be. It's just how many moles is present is what went into that PV equals nRT equation. So yeah, basically you can plug in any mole amount, or the mole amount of the same amount of gases. So like if we look at this graph here, if we plug in PV equals nRT for any one of these substances, we see that ammonia, nitrogen, helium, hydrogen, they all exert or occupy the same volume when they have the same mole amounts. We see some small deviations in these other substances because we can't consider chlorine gas or CO2 as an ideal gas. We actually need to consider their real deviations from the kinetic molecular theory. We need to consider some of those details there for these larger molecules. So for real gases such as chlorine or CO2, we can't use the ideal gas law, PV equals nRT, to directly correlate into pressure, moles, and volume. We have to use the van der Waals equation, which looks a little bit scary. There's a bunch of terms, extra terms in there, but I like to just think of it as it's the ideal gas law with some sprinkles on it, where we have this P term with an adjustment. We have our V term with a small adjustment equals nRT. It's the same stuff as before. We just need to make some small adjustments to pressure and volume depending on the identity of our sample. Because what we'll see here is at high pressure or low temperatures, we see deviations from pressure, the true measured pressure, true measured volume, depending on our sample. So I showed some examples of like how samples will deviate depending on their temperature and pressure. We see at high temperature, a sample will exhibit more ideal-like behavior. At low temperatures, a sample will exhibit more ideal-like behaviors. And so again, this kind of reinforces our non-ideal conditions, our high pressure and low temperature, where we can use the ideal gas law for low pressure and high temperature, which I like to just kind of loosely define as like earthly conditions. On Earth, we have 1 atmosphere pressure. That's fairly low. We also have a fairly high temperature at 298 Kelvin. That's fairly high. So basically, everything other than earthly conditions is real conditions. All right, so those are examples of our deviations from the ideal gas law. Now, if you looked closer at the van der Waals equation, we have these A and B terms within there that we use to adjust. And so the trends that we see here, the A term is related to attractions, which we'll talk about in chapter 11, and the B term is related to size. Typically what we see is as B increases, the size of your molecule increases, the A term also increases. That's a typical trend that you'll see. And so this kind of reinforces the idea, if we go back to this slide, slide or this graph is that the heaviest gases deviate the most, that we have to actually use the van der Waals equation to calculate the pressures and volumes of these two substances because they're so large. Their B terms are quite significant. So we looked into the consequence and the details of each of those terms. So first let's look at B. That B term within our van der Waals equation dominates at high pressures. So if we think about how can we get a sample to exhibit a high pressure, we have to shove a bunch of gas particles in a small space. So if you put a bunch of gas particles in a small space, there's tons of particles, they start to actually take up space in the container itself. So we can no longer assume that the volume that the gas particles freely occupy is the actual volume of the container, because you've shoved so many particles in that small space, the particles themselves start to take up some of the free space in the container. So that's what this minus NB term is. We're subtracting the amount of space that the particles actually occupy. So then this whole like adjustment term is what we place into our ideal gas law. And that's how we get closer to the van der Waals equation. And so this term, this minus NB part, is fairly important when you are working with a ton of moles of gas. So meaning at a high pressure, that this N term, it's the same N as number of moles, that when we subtract, a large number here, the change in volume is significant when we use the van der Waals equation. So B term dominates at high pressure because you're shoving a ton of particles in that same space. And we can no longer assume that the gas particles do not take up space. And so the other term, right, so B is applied to size. So larger particles will take up more space. The A term is related to attractions. So I like to think of it as we're addressing the kinetic molecular theory postulate, where we make the assumption that attractive forces between gas particles, there is no attractive forces. They're just kind of bouncing off one another like crazy billiard balls. But what the van der Waals equation is supposing, hey, maybe they do interact with one another. Maybe they are attracted to one another. So I like to think of it as, okay, the gas particles, we're considering their attractions. They're still bouncing off one another, but the collisions are inelastic. So when they bounce off one another, they're just kind of sticky. So they stick a little bit, so when they bounce off one another, they're not converting all of that energy into kinetic energy in the other direction. So I like to think the particles, they're sticking more to each other, so they're colliding less with the outer walls of the container. That's how I like to think of it. So I think if we look here at the kind of conclusion, if the molecules are attracted to one another, they make fewer collisions with the actual container. So we observe a lower pressure than typical because the particles are attracted to one another. They're less attracted to the outer walls of the container, which is directly related to the pressure. All right, and so how we adjust for it is with this term, that the pressure that we actually measure is adjusted from the ideal pressure, where we take into account the attractions term and how many particles are present per volume. So yeah, and so at low temperature, this attraction term dominates because the particles aren't moving very fast already. So if they're not moving very fast and they're sticky, they're more likely to stick and make a bigger difference in kinetic energy in that regard. If they're already moving super fast, a small amount of stickiness won't make a big difference. So that's why, again, reinforcing at low pressure, or sorry, not low pressure, low temperature, real gases kind of come into play. All right, so A term, B term, we put it all together. That's how we get the van der Waals equation. It's the same equation I presented above, but I just kind of wanted to, explain, why we have to use this equation when we have high pressure conditions or low temperature conditions. And it's because of the ideas of kinetic molecular theory breaking down, and we can no longer use the ideal gas law. So then we have these just small adjustments that we make to the equation, all right? So for any gas, we can actually calculate the predicted pressure using the ideal gas law equation and the van der Waals equation. So I think that's what we're doing next, yes. All right, so we learned about the ideal gas law, the van der Waals equation, so let's do that. So let's calculate the pressure that's exerted by 1 mole of CO2 at this volume and this pressure according to 1, the ideal gas law, and then 2, using non-ideal behavior. So that means we use the van der Waals equation. Okay, so if we go through the givens here, 1.00 moles, that's N. 1.00 liters, that's our volume there, and 298 Kelvin, that's our temperature. So here we're calculating for volume. So the first one's fairly easy. We're just plugging those values into the ideal gas law, right? PV equals nRT, we're just solving for P in this case. So pressure equals nRT over V equals, so let's put in those numbers, 1.00 moles, R 0.08206 liter ATM mole Kelvin, temperature 298 Kelvin, and over volume is 1 liter. All right, so plug that into your calculator, you get, oh, I already have it there, 24.4. Hopefully that's right, 24.4 ATM. So that's just plug and chug, PV equals nRT. We've done a billion of those already. Now the harder part, the more tedious part, is doing the van der Waals equation. So what I want you to recognize here is that we have to give you the A and the B terms in order for you to solve these things. So it's just a little bit more tedious to do real gas or van der Waals equation thing. So here's the van der Waals equation. If we look through what's given, we have all of the pieces we need. The new pieces of information that we're going to use are the A and B terms that are given for CO2. All right, so it's just very tedious. What we're still calculating for pressure, we just need to put in those A and B terms and mole amounts and volumes where necessary. So this is just a tedious calculation. So we're solving for pressure. So plus N squared, so moles squared. I'm just gonna drop my units because I'm lazy. So our A term, 3.59 over volume squared, so just 1 squared, 1 liter squared. All right, so all of that in parentheses, that's my adjusted pressure term, times the volume, the new van der Waals volume term. So volume, oh wait, we were given what volume? So 1 liter minus N, so 1 mole, times the B term, so 0.0427, all right, equals nRT. So 1 mole times R, it's the same R we've always used. I'll just write it, 0.08206 times temperature, 298. So yeah, this is tedious. I hope I have, do I have the numbers? I hope I do. Do I? No, I don't. Okay, great. So what I will typically do is just multiply the terms on the nRT side together. I will do the subtraction for the volume term and calculate this. So pressure plus, there's just a bunch of ones, so 3.59, parentheses. So 1 minus 0.0427. So the new volume term is 0.9573. So what that basically means is that if our tank is 1 liter, all right, and we have 1 mole of CO2 in it, if we consider the actual volume of the particles themselves, there's actually only 0.95 liters of space for those gas particles to actually bounce around in. So that's what that subtraction term is. Equals 0.08206 times 298. Whoops, equals 24.45. All right, so I'm going to divide both sides by that term, so divided by 0.9573. So I get 25.54 equals pressure plus 3.59. All right, and so if you subtract that 3.59, you will get that the pressure using the van der Waals equation is 22 atmospheres instead. So this is us considering the actual volume of the particles themselves and the attractive forces that CO2 exhibits. So we get a value that's just a little bit different. a little bit different. So 22 instead of the typical 24.4 atmospheres that the ideal gas law would calculate. So that is tedious. Would you agree that the calculation is tedious? I have to give you A, I have to give you B, just put in the numbers, make sure they're the right unit, and do the arithmetic crunching there. So I will show you this last question is an example. It's a problem with absolutely no calculations. All right, you shouldn't have to calculate anything. So here's the situation. You have two separate identical containers at the same temperature. You have one container that contains 1 mole of nitrogen gas, and you have another container that has 1 mole of CO gas. Assuming both molecules are relatively the same size, if we consider these containers to be real gases, which container has the higher measured pressure? Don't look at the answer in the corner. Don't look at the answer. There we go. Which one? So this requires no calculation. So if we kind of read through what I mentioned, so when we think about real gases, we think about the size of the particles, we think about the attractions. So we have the same mole amount of gas in each of the containers. Their identity is different though. If you read through it, I say they're the same size. So which term should be around the same number for each of them, A or B? B, if the sizes are the same, so that leaves just the A term. A stands for attractions. So we need to think about how the attractions of these particles differ, all right, to answer this question. So if you consider attractions of the molecules to one another, which one will exert a higher pressure? Which one's going to be bouncing off the walls of the container more? N2 or CO? N2 or CO? What do we think? How about you whisper it to someone? Whisper it to someone. What do we think? If we consider attractions, just break it down. Break it down. What's the difference between nitrogen gas and CO? One is polar, one is non-polar. So which one's going to exhibit more attractions to one another? CO. CO is going to be more attracted. So if they're more attracted to one another, they're bouncing off the walls of the container less because they're hugging one another. So they're not bouncing off the container. So now, which container has the higher pressure? N2, yes it does, yes, it's N2, because in CO, they're like little magnets. They're more attracted to one another and not to the walls of the container, yeah? Versus N2, there's a very small amount of attractions, so they're gonna bounce off the walls of the container, no problem. Good? So no calculations, but that was a tricky one, wasn't it? Okay, all right, okay, so we're done. Would you rather do this one or the calculations? Calculations, too bad, too bad. We like to ask these types of questions because they're quicker, all right? Because we recognize that the tedious calculations, like we can fit more exam questions in a final exam when it's conceptual this way versus a mathematical one. But the math, you should be able to understand the math too, and see that our trends here will match there. All right, so what was my answer here? N2, because CO has more attractions. CO is overall polar. Great. All right, so that's chapter 10. That's it. So that means homework is due on Sunday. All right, so we're going to move on to chapter 11. Yay. Okay, so chapter 11, so 10 we talked about gases, so we're just going on through the phases. We did gases. Next, we're going to do liquids. In chapter 12, we're going to talk about solids. So what's going to come back and haunt us in chapter 11 is Lewis structures, molecular geometry, and polarity. So that last question we just did, we compared the overall attractions or polarity of N2 versus CO. We're going to be doing that constantly for this whole chapter, for chapter 11. I will say this is one of the most important chapters going into chemistry 1220. So if you're going to be taking 1220 in the spring, this chapter and chapter 12, because we're reinforcing the ideas of applying Lewis structures, molecular geometry, polarity to observable things. That's going to be super important in chapter 13, which you will do in 1220. All right, so do review those things, Lewis structures, geometry, and predicting polarity of molecules. So we'll look into some of the details that go into predicting whether we see a gas, liquid, or solid of a sample at room temperature and pressure. Basically, the ideas of attractions between molecules is what described in intermolecular forces, and it's those forces that dictate a lot of different properties that we see. So this chapter perfectly encompasses what I call the secret to chemistry, is that composition and structure is what dictates the chemical properties and behaviors that we see. So this chapter really reinforces that. So the different properties that are basically affected by intermolecular forces, we will also talk about. All right, so let's think about something as simple as the states of matter that we talked about in chapter 1. We talk about solids, liquids, and gases. We already talked about gases. Now we're moving on our way to liquids. So it's funny, like, why does liquids have its own chapter? Because when we think about the matter that we interact with in our everyday life, like when you think about it, like we breathe oxygen. Oxygen's a gas. But like, why is it a gas? Versus water, H2O, we drink it every day because it's a liquid, right? Why is water a liquid at room temperature and pressure? You ever think about that? It just is. It's just a liquid. But really, what it has to do with energy. There's this constant battle between kinetic energy of the particles in your sample versus the attractive forces keeping your sample together in the condensed phase. So it's this battle between kinetic energy and potential energy. That's basically all of chemistry and physics in general, but there's some details here within attractive forces of particles that we haven't really talked about, that specifically intermolecular forces. So basically, when I talk about the battle between kinetic and potential energy, remember, we talk about kinetic energy of our sample. The average kinetic energy is related to the temperature of our sample. So we're constantly going to be talking about temperature of our sample and comparing that to the attractive forces present in our sample. And so that is related to intermolecular forces, and I will give you the tools of how we determine that. So when we think about attractions and potential energy, we're going to use the same equation here, all right? Q1, Q2 over distance. Remember this equation where we have what kind of forces are at the top of this graph? Attractions or repulsions? Repulsion, so we could have like 2 positives or 2 negatives or something. But what we are going to care about here more is the attractions part, that things are highly attracted to one another when they have a low potential energy, when those particles are close together. So intermolecular forces is related to the bottom part of our potential energy diagram. Attractions, oppositely charged things are attracted to one another. All right, so keep those things in mind: temperature, and particle attractions. And that's what dictates a lot of properties we see. All right, so for example, some of the properties that we see, a really great example of intermolecular forces dictating properties we see are some of the halogens, the gases, the halogen gases. If we look at chlorine gas, bromine gas, and iodine gas, so Cl2, Br2, I2. Those molecules at room temperature and pressure, so all at the same temperature, they adopt different phases. Chlorine gas is a gas. Bromine is actually a liquid at room temperature, while iodine is a solid at room temperature. So that's that's a weird thing, all right? That's a really weird thing, and this is a great example of how intermolecular forces come into play. So when we think about gases such as Cl2, we can think about, their packing, their motion. We have free motion here. We've already talked about this. Let's try to use our intuition here and think about the balance between kinetic energy and attractions via intermolecular forces. Which one do you think dominates when we look at a gas sample? Kinetic energy or intermolecular forces or attractions of the particles to one another? Which one dominates? Kinetic energy, yeah. So look, there's free motion. There's free motion. So those particles are bouncing off the walls. So that means that there's excess kinetic energy to overcome all of those attractive forces, like in chlorine gas. So chlorine gas has a small amount of attractive forces between its molecules. Let's go on the other side, a solid. So iodine here is a solid at room temperature. So same amount of kinetic energy is there. But this substance adopts a solid. Weird. So let's think about the details of a solid. Packed, highly ordered. There's very little motion. There's just vibrational motion, typically for solids. So the same idea. If the battle between kinetic energy and intermolecular forces, which one's winning in a solid? Yeah, intermolecular forces, because intermolecular forces are particle attractions. In the solid phase, the particles are close together. They're attracted towards one another. And then finally, in the liquid phase, it's still the condensed phase, but there is more motion, translational motion. Particles can move past one another, but they can't just bounce off the whole walls of the container like a gas can. So I like to say kinetic energy and the attractions and intermolecular forces, they're on the same order, that they're similar in energies versus in a gas, kinetic energy wins, in a solid, IMFs win. All right, and so those are some examples of different properties we see. All right, so I want to relate the idea of attractions and kind of build its significance in the context of the observations we can make to something we've talked about before, just today, where we talked about our A and B terms in the van der Waals equation. I mentioned before, when B, the size of the molecule increases, we typically saw an increase in the A attraction term. And there's a reason, and it's based upon one of our intermolecular forces that we talk about. So if I graphed all of these things, if I graphed the B term versus the A term, what you'll see is a very nice straight line where we basically say as B increases, A increases too. So all of those data points fit on that trend really, really well. But there's some weird ones like water. Water kind of falls off the graph, and we'll learn here soon why. But basically all of these dots that lie on the, okay, as B increases, A increases, has to do with London dispersion forces, one of our weakest intermolecular forces that relate size or molar mass of a sample to its attractions. And then we'll also explain why water is so weird off to the side here. All right, so let's talk about intermolecular forces. There's a lot here, I'm sorry. Okay, so I'll spend some time on this slide. So intermolecular forces, it's molecule attractions. So in terms of attractions, we're still talking about the same attractions we got from potential energy. We have charges, right? In this case, since it's attractions, we're talking about oppositely charged things being attracted towards one another. So just think of intermolecular forces are attractions, oppositely charged things. So there's kind of two ways that we can get charges to have them be attracted to one another. We've already talked about full-blown ionic charges like sodium chloride, that's a +1 and a -1. So we can have full charges being attracted towards one another. We already talked about that in terms of like lattice energy, forming ionic compounds, yeah. But we can also have attractions between not full-blown charges, but partial charges as well. So remember the way we denote partial charge is with our little delta sign here. So you can have a partial positive and a partial negative attracted to one another too. It's a weaker attraction, but it's still an attraction nonetheless. So this is an example of an intermolecular force where the partially positive side of HCl, so that hydrogen is partially positive, the chloride is partially negative because of differences in electronegativity. So I told you we're bringing back chapter 8 and 9 stuff. And so those partial charges can be attracted towards one another, just like the way we said, oh, sodium plus and chloride minus, they can be attracted towards one another too. All right, it's just two different schools of thought. One's between full-blown, like full charges, one's between partial charges. All right, So just think oppositely charged things, and that the charges can come from a myriad of sources. So intermolecular forces are important because they control a lot of the properties that we'll see here and we'll talk about here soon. I want to address the detail here of intermolecular forces and how this differs between like chapter 8 and 9 material that we went over. In 8 and 9, we talked about chemical bonding. Chemical bonding, like covalent bonding, ionic bonding, that those are bonds formed to make a molecule, all right? So like covalent bonds occur between bonded atoms in the same molecule. But intermolecular forces, these are attractions between different molecules, but in the same sample. All right, so we're kind of taking a step back. In chapter 8 and 9, we looked at, okay, what creates a molecule? How can we bring atoms together to form these bonds? Intermolecular forces are just attractions between different molecules. They're weaker, but strong enough to dictate a lot of properties. So that's the distinction I want us to be thinking about here. It's attractions between different molecules. And we'll consider 4 main types of intermolecular forces. There's 4 of them here. The first one, London dispersion forces, is the weakest. Ion-dipole interactions are the strongest. And then I have here what to look for. We'll go into detail with all of them. So intermolecular forces, attractions, be on the lookout. Where are the partial charges coming from? And oftentimes the name of the intermolecular force tells you what kind of attraction is happening or what kind of charges are involved. So let's talk about the first one, London dispersion forces. This is the weakest one, right? We oftentimes call it LDF or sometimes just dispersion. We'll call it that. All right, so this one's the weakest one, and it's the most important IMF in nonpolar compounds. And it's important because nonpolar compounds only exhibit London dispersion forces, and atoms. Like if you think of like helium, neon, krypton, those types of things, those are all nonpolar atoms. Those particles still exhibit attractions, but it's via the weakest one, the one that we're talking about now, London dispersion. All right. So I'll just tell you what the trend is now and then explain like where the attractions come from, because it's weird. These are nonpolar substances. There are no charges, right? And so when we think about IMFs, intermolecular forces, I said, okay, we have to have charges present. But in nonpolar compounds, are there any charges present? No, there aren't. So partial charges come up in a different way. So the trend for London dispersion is that the attraction for London dispersion increases as the weight of the molecule increases or as the surface area increases. So, so I mentioned nonpolar substances don't have any charges. They don't. Or all of their bond dipoles cancel out. So where do those charges come from? They come from temporary dipoles that are created. So if we look at this picture here, here are 2 helium atoms, right? Helium is a nonpolar atom. It's literally just an atom. But when we think about it, helium, it possesses 2 electrons, right? Each helium atom possesses 2 electrons. Do those 2 electrons, do they stay in one place or are they zipping around randomly? What do we think? Do we know for certain where an electron on helium is at any time? No, because that violates the uncertainty principle, right? We can't know its position. So really, the electrons on a helium atom, they're zipping around randomly all the time. All right, so just keep that in your mind. They're zipping around randomly. So if we, for a second, just took a picture of the helium atom and for a second just located where those 2 electrons are, at any one point, we could have those 2 electrons. They could be like opposite of one another, kind of evenly dispersed around the atom. So the negative charge is kind of like, evenly dispersed around the atom. But if we take a picture at another instance of time. Maybe those 2 electrons, since they are zipping around randomly at a certain instance of time, are on the same side of the atom. So if we look at this atom right here, do you see a unequal distribution of charge here? Yeah, because we have electrons that are partially, on one side of the atom. And then what is this black dot? Is that black dot something? That's the nucleus, and that is what charge? Partially positive. So at any one instance, temporarily, the electrons can just be located on one side of the atom at any certain time. And what happens is that you can induce, with that temporary dipole, induce another dipole in a neighboring atom. Because if you are an electron over here and you're looking at this other helium atom that has a temporary dipole, are you attracted to any certain part of the neighboring helium? You should be. So this temporary dipole can induce another dipole in a neighboring atom. So like this electron will be attracted to the partially positive side of that neighboring helium atom. So this type of attraction isn't as obvious as like a sodium cation and a chloride anion. This is a temporary dipole. It just happens for a split second in time and then it goes away. And so that's why we say London dispersion forces is a very weak attraction, because it only happens for an instant moment in time, basically due to the fact of like statistics that at any one time electrons can just be on isolated on one side of the atom more than the other side and induce a dipole in a neighboring atom. So yeah, so that's all that's there. So if we look back at the trend here, I said LDF, this dispersion, this phenomena increases as the molar mass increases. So if we looked at helium versus neon, neon should have more London dispersion attractions towards one another. So let's think about it. So neon, because it's heavier, right? There's more protons on a neon atom. If there's more protons, there's also more what? Electrons. So really the trend is the more electrons there are in your molecule, the more likely, because of statistics, you will produce temporary dipoles when you have more electrons. So that's where this trend comes from. Dispersion, important in nonpolar compounds, because you can, in fact, produce a temporary dipole when you have a lot of electrons. That happens more. So you'll see as molar mass increases, LDF increases. We also see a trend in surface area. I think that's on the next slide. All right. Okay, so the idea here with London dispersion, all substances actually exhibit London dispersion, whether it's polar or nonpolar, but nonpolar substances, LDF is the most important because that's the only attraction present. For polar molecules, we have more attractions that we can talk about. So where this trend comes from is from the idea of polarizability, which will be important in organic chemistry when you take it. So the idea of polarizability is the ease at which electrons can be distorted. And so that directly relates into the idea of producing a temporary dipole, which relates to London dispersion attractions. So a substance that is more polarizable is able to exhibit more London dispersion because it can produce a temporary dipole quite easily. And so the factors, and I already mentioned, polarizability will increase when surface area increases, or the weight or the molar mass of your substance increases as well. So surface area, if we think about the ease at which polarizability can occur, long skinny molecules have more surface area. They have more surface area, so they exhibit stronger attractions towards one another. So linear molecules have more surface area, while spherical have less surface area. And due to surface area, spherical molecules will have the least amount of London dispersion attractions. So long skinny molecules are more attracted towards one another than spherical molecules. That's what I'm trying to say. And so this example, I'm showing two molecules that have the exact same weight. They're isomers. I think both of them, 5 carbons, 12 hydrogens. Yeah, both of them have the same formula. It's just how they're connected is a little bit different. So their surface area is a little bit different. So therefore their London dispersion is a little bit different. And they have a difference in boiling points here, which we'll talk about in a minute here. So This example showcases surface area and how that can address London dispersion. Weight also, we looked at helium and neon. Neon has more electrons, will exhibit more London dispersion. So if we look at our chlorine, bromine, iodine examples as well, again, we can see the trend, again, the molar masses of diatomic chlorine, bromine, iodine, it increases. If we look at their boiling point temperatures, we see they also increase. And that's because iodine, because it's the heaviest, has the largest amount of IMFs present in the form of London dispersion, because all those particles are nonpolar there. And so the boiling point temperature increases, and that directly affects our observations, because we said at room temperature, chlorine is a gas, bromine is a liquid, and iodine is a solid. All right, so that's London dispersion. And so I kind of mentioned it here, how we oftentimes will look at the degree and magnitude of intermolecular forces in a sample by looking at boiling point data. So remember, IMFs, intermolecular forces, where do they occur? Between atoms in a molecule or between molecules? Between molecules, yes. So when we boil something, boil water, what are you breaking when you boil water? When you turn a liquid to a gas? Do you break covalent bonds or do you break intermolecular forces? Yeah, you break the attractions between molecules, because remember, boiling water is what, a chemical or physical change? Physical. So we're not breaking any chemical bonds. We're not breaking any covalent bonds here. So the idea of boiling point data tells us directly how the degree or the amount or magnitude of intermolecular forces present in your sample. Because when you think about it, when you have a liquid, right, the intermolecular forces present in your sample are around the same order as the kinetic energy. But when you boil something, you add so much kinetic energy that you break all of the intermolecular forces to make a gas. So that's how we can directly correlate intermolecular forces with something we can actually measure, boiling point data. So more energy to make it boil, it means that there's more intermolecular forces present in that sample. So in this graph, you can see that directly here. Fluorine, chlorine, bromine, iodine. See how as the molecules get heavier, the boiling point goes up. Same thing with the halogens, neon, argon, krypton, xenon. Again, as the atoms of those substances get heavier, the boiling point data goes up. And so again, that directly is related to London dispersion forces. As molar mass increases, we typically see more LDF attractions. All right. But remember, shape also plays a role with LDF. Let's compare the boiling point temperature of chlorine and xenon. So chlorine weighs 71 AMU, xenon weighs 130 AMU, and here's the boiling point data. So just based on the numbers, which sample possesses more intermolecular forces attractions, chlorine or xenon? Remember, IMFs, the big idea, as IMF increases, boiling point temperature increases. So which one has more intermolecular forces present? Chlorine, yes. Chlorine, because it has a higher boiling point, right? Has a higher boiling point temperature. So tell me, what explains that difference? The molar mass difference or the surface area difference? What do we think? What do we think? Why don't you whisper it to someone? Why don't you whisper it to someone? So just pick one and see, does it agree with the trends that we see? If not, then choose the other one, right? So this one's a little bit weird, right? It's weird. In all of the graph, didn't I say, oh, as molar mass increase, boiling point increases, right? But in this one where I compare chlorine gas and xenon, chlorine, the lighter one, actually has the higher boiling point. So that substance has more intermolecular forces present. But it's the lighter one, so that means molar mass cannot describe that difference. So what's the only other option? Surface area. So if we think about surface area, all right? Diatomic chlorine has double the surface area than a xenon atom. So yeah, the answer here is surface area. Chlorine has more surface area because it's a diatomic molecule. Yeah. So don't automatically think that LDF is related to molar mass. It is when the molar mass difference is like really, really, really big, all right? But in this case, it's actually surface area that it makes the difference here, okay? So I tricked you. All right, so let's look at some more stuff here. All right, let's look at the boiling point data of these molecules. Boop, 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 boop. Okay. Which substance has the most intermolecular forces based upon the boiling point data? Which substance are the particles attracted the most towards one another? Acetonitrile, right? Because this one has the highest boiling point, it's going to have the greatest amount of IMFs. And then which one has the lowest IMFs present? Based upon boiling point data. Propane has the least amount of IMFs. Okay, great. So we just learned about London dispersion forces. Look at their molar masses there. Do molar masses explain the difference in boiling point data? No, they don't. Yeah, so what we see is we see a gradual increase in boiling point data. The molar masses are basically all the same. They're basically all the same. They're all around 40 grams per mole. But what is different is, do you remember what this symbol is? A little mu? Dipole moment, yeah. So what we see here, don't focus on molar mass here, because we're not talking about London dispersion anymore. We're going on to the next intermolecular force, and that's dipole-dipole attractions. So what we see does trend really, really well with the boiling point data is the extent of the dipole moment, the permanent dipole moment in all of these molecules. So what we see here, propane has basically a non-existent dipole moment. There's my dipole arrow. Versus acetonitrile has a huge dipole arrow. It's like almost 4 dipole. Versus acetaldehyde has a slightly smaller dipole arrow. Dimethyl ether has an even smaller dipole arrow, right? And so what we see here is as your permanent dipole increases in these molecules, you can think of them as little magnets, okay? So if they're little magnets and they're highly attracted towards one another, you gotta put a ton of energy to boil it because you break all of the intermolecular forces present in the sample, all right? Okay, does LDF explain BP? No. No, okay, great. So let's talk about that attraction, dipole-dipole attractions. So we talked about LDF being really important in nonpolar substances. Only polar substances can exhibit dipole-dipole attractions because the name already says it, dipole. It's a dipole interacting with a dipole, a permanent dipole interacting with a permanent dipole. Only polar molecules have permanent dipoles. So that's what you want to be looking for here. All right, permanent dipole. So here's the example of acetonitrile. The red lines are your dipole-dipole attractions here. See how they're between molecules? The atoms here connected, those are our covalent bonds. So when we boil acetonitrile, we are only breaking those attractive forces there. So again, just think of all of these particles, because there's a permanent dipole, they're just little permanent magnets that are attracted towards one another. So when you want to boil something that is polar versus another molecule that's nonpolar, the polar molecule will almost always have the higher boiling point because we have to get past these dipole-dipole attractions for the most part. All right, so we need, that's what we're looking for, permanent dipoles here. So let's look at some examples because I always think those are better here. So I have some examples here, fluorine, argon, HCl, and H2S. So I have their molar masses here. So let's just look at these examples and identify, are they polar or nonpolar? So diatomic fluorine, polar or nonpolar? Nonpolar, yes, okay. Argon. Non-polar, it's just an atom. HCl, polar, yes. How about H2S? I even have the Lewis structure here for you. It is polar because if you drew it linear, then you might think it's nonpolar, but because it's bent, H2S, because it looks like water, is polar. Okay, so if we look at like the polar group versus the nonpolar group, look at their boiling point data. See, the nonpolar substances have much, much lower boiling points versus the polar substances, much higher boiling points. Because if you look really closely here at the molar masses, they're basically all the same. All right, so these differences in molar masses aren't going to explain this boiling point data, but what is the molecular polarity. So we actually have to consider, unfortunately, their structure in order to describe this boiling point data. So let's look at another example here, acetone and butane. And then look at these boiling point data here. So without actually looking at the molecules, if this is the boiling point, so 56 Celsius and basically 0 degrees Celsius, which substance has more intermolecular forces present based upon boiling point data? Remember, higher boiling point, more intermolecular forces, more attraction. So which one has more IMFs? Yes, the acetone, because its boiling point data is higher. But let's list all of the IMFs present in those two molecules. So let's do the first one, LDF. Do both of them exhibit LDF? That's a trick question. Everything exhibits LDF. So yes, they do. Both of them exhibit LDF. Is any one more than the other if we look at their molar masses? They're actually the same because both of them have the exact same molar mass, 58. I tried to pick two that were the same size relatively. They have the same LDF. But now let's consider the next intermolecular force that we're discussing here. Does butane exhibit dipole-dipole? No, it doesn't. Everything, it's a high, oh, sorry, that's a, okay, no. Everything is a non-polar bond. We have carbons attached to carbons, carbons attached to hydrogens. Those are all non-polar covalent bonds. Butane is a non-polar compound. All hydrocarbons are non-polar. But if we look at acetone, is dipole-dipole present? Yes, and I tried to make it obvious by showing the partial charges here. All right, that acetone molecules do have permanent dipoles, so they're going to exhibit more attractions than something that's nonpolar. So when we list these IMFs, is that consistent with the boiling point data? Yes, it is. Okay, great. All right, so if you haven't noticed already, boiling point is a really good indication of total intermolecular forces in our sample. We already looked at it going down a group, like neon, argon, krypton. We saw boiling point increase. Fluorine, chlorine, bromine. Boiling point increase. So let's look at some other ideas too. So again, molar mass usually indicates the extent of intermolecular forces. We can see that here with different compounds, all right, that have hydrogens bonded to them. So like going from silicon or CH4, silicon, germanium, tin with hydrogens attached there, the boiling point data just goes up as we go down the group. All right, within group 4. But if we look at the other groups 5, 6, and 7, when we attach hydrogens to it, we see that, you know, molar mass and boiling point trend only kind of works over here. What we have some really weird data over here, where we have water, HF, NH3, it looks like they have unusually high boiling points for their placement, that they don't fit this big idea as IMF increases, or sorry, not the big idea. It doesn't follow the whole idea of molar mass increasing, boiling point increasing. Water, HF, and ammonia are fairly light molecules, but they exhibit unusually high boiling points. And this segues us into the third intermolecular force that can take over past dipole-dipole, and that is hydrogen bonding. Hydrogen bonding is happening between water, HF, and NH3, and there's a certain criteria that we have to kind of have in order for hydrogen bonding to occur, and I will show you down here. So basically, hydrogen bonding is a very, very special dipole-dipole attraction. It's a dipole-dipole attraction where you produce a very electropositive hydrogen atom. So a very positive hydrogen atom. And so the criteria that you want to look for here is a hydrogen that's highly polar, so highly electropositive. And so typically you do that by attaching it to a really electronegative atom, and then that atom needs to have a lone pair of electrons on it. So this is what you want to write down over here. This is what you want to look for. All of these hydrogens can participate in hydrogen bonding. So a hydrogen attached to an oxygen, a hydrogen attached to a nitrogen. Usually nitrogen has 3 bonds, so there should be another bond there. But it doesn't matter what that nitrogen is. We just need at least 1 hydrogen and a hydrogen attached to fluorine. So this is what you want to look for this special case dipole-dipole attraction that we call hydrogen bonding, and it is unusually strong. And we'll talk more about this on Wednesday.